welcome to the class of antenna and propagation. And here we will discuss the different types of antennas. And in the different types of antenna, we will discuss about the Yaguda antenna and the long wire antennas. And in the long wire antenna, we will discuss about the its types. Clear? So Yaguda antenna is the most commonly antenna which is used for TV receptions. In the earlier days, we used to have a Yaguda antenna instead of the parabolic antennas. So in the today's time, we are using the parabolic reflector antennas for the TV receptions or the internet purpose. Clear? So in the earlier time, we used to have a Yaguda antenna which is mainly used for the TV reception over a clear. And why it is most popular? Because it is easy to use and it is used for its high gain and directivity. Clear? The frequency in which the Yaguda antenna operate is around 30 megahertz to 3 gigahertz, which is belongs to the VHF and UHF band. Clear? So Yaguda antenna mainly have three elements. First element is driven element. Why it is known as the driven element? Because the main current or main power supply is given to this element, and from this element the other elements get excited. The second is your directors, and third one is your reflector. Clear? And this driven element in which we used to give the main supply, that is also known as the active element, and director and reflectors are work on the get the excitation from the driven element. So these are known as the parasitic element. Clear? So this is the Yaguda antenna, and in which this is a stand and this is a dipole, or this is a driven element. This driven element may be dipole of any type, lambda by 2 dipole, or it may be the folded dipole antenna. Clear? And these are the directors. On increasing the directors, we will get the higher gain and the directivity. And this reflector is having its unique function of increasing the directivity also. Clear? So the Yaguda antenna has a dipole which is the main radiating or driven element. Further, the other are the parasitic elements which are not directly connected to the driven element. So these parasitic elements pick up the power from the dipole and we radiate it from. Clear? The phase in such a manner, they are adjusted in such a manner that they are causing the power to be focused in particular one direction and removed from the others. Means these parasitic elements are arranged in such a distance such that the whole power is giving into the particular direction and removed from the other direction. Whole power कह सकते हो, or you can say the whole signal. These parasitic elements of the Yaguda antenna operate by re-radiating signals in a slightly different phase to that of the driven element. Clear? So three elements mainly, that is driven element. It is normally a half wave dipole or often folded dipole, another one is reflector antenna. This is only one having a reflector. The Yaguda generally have a one reflector. It may have a one or two reflectors, and this is placed behind the main driver element. Remember, this is placed behind the main driver element, and this reflector behind the first one add little to the performance. Means it will increase the directivity of antenna. Clear? And this director is also having a most important role in increasing the directivity and the gain of antenna. Clear? So these directors are placed in front of the driven element, and in the direction of maximum sensitivity, each director will add around 1 dB of gain in the forward direction and reduces the, because although this level reduces as the number of directors increases. Clear? Now see this one. If I say this is the only Yaguda, this is only a dipole. If I say this is radiates in this direction, so this will be a bidirectional antenna. But when I have placed the dipole, when I have placed the directors in front of the dipole and reflector in behind the dipole, then the radiation pattern becomes what? Unidirectional. Clear? Now see why it is becomes the unidirectional, because this dipole, this director increases the directivity of this dipole, and the power which is this driven element radiates the power in this direction, but the power which is obtained, which is getting at the reflector by the dipole, it's get reflected and to the forward direction. That's why its radiation pattern is unidirectional. Clear? With higher directivity, and very practically this will have a very less amount of back lobe. Clear? So this one Yaguda antenna is, this one is the unidirectional. So what is the difference between the Yaguda antenna and the normal dipole, half wave dipole? That because the difference is that normal half wave dipole is bidirectional antenna and Yaguda antenna is the unidirectional, and it also have a higher gain and higher directivity with respect to the normal dipole. Clear? So the basic element is used in the Yaguda antenna is the half wave dipole, which is placed horizontally along a, is known as the driven element. Clear? Now to have a director, the length of the director is always less than the main driven element. So in order to make the unidirectional, additional rod elements are placed on either side of the dipole antenna. Means it can be placed in the front and it can be placed in the director, and these are known as the parasitic elements. Clear? The elements which have a longer length, the elements have a length longer than the dipole are known as the reflector. You will see here that the length of this reflector is always greater than the length of the driven element. Clear? And the elements having length less than the driven element is placed in front of the driven element is known as the directors. Clear? So the design equations for designing a Yaguda antenna is, first is, if I say that if I want to calculate the reflector length, then reflector length will be equal to 152 divided by frequency, and that frequency should be in the megahertz. Now to calculate, now for designing the reflector antenna, the Yaguda antenna, the driven element length should be what? 143 divided by f in megahertz. The first director length will be 137 by f, and second director length will be 134 divided by s, and the length of successive directors will reduces by 2.5%. Clear? And the spacing, this we have find out, length we have find out, what is this length will have a 152 divided by 5 f. This have a 143 divided by f. This have a length of 137 divided by f. This have a length of 134 divided by f. Frequency is what? In megahertz. Remember this one. Clear? And this length, this directional length is further reduces by 2.5%, means 97.5% of 134 by f. That will be the length of the third director. Now another design equation is this one. We want to have a distance between, what should be the distance between the reflector and dipole and the dipole and directors. So reflector and dipole spacing should be, that will be equal to 0.25 lambda, where lambda is equal to what? C by f. Clear? And spacing between the direct and dipole, that will be 0.13 lambda, and spacing between the direct and director should be 0.13 lambda. Is this spacing should be 0.25 of lambda, and this spacing should be of 0.13 lambda. Clear? Now see this one, or you can say that length of director is 4% less than the length of director. Length of director is 4% less than the length of dipole or driven element. Clear? Now the length of dipole and length of reflector is always 5% more than the length of the driven element. Now see the length of dipole, that is L equal to lambda by 2. Put the lambda equal to C by F. Put this one value, that comes out to. Now see, if I want to design a Yaguda antenna with the center frequency of 65 megahertz, means it should radiate at 65 megahertz. So what will F will be what? 65. Put this value, length of dipole lambda by 2 C by F, that is equal to this one. You will get the length of dipole should be 2.31 meter. Now we want to find out the length of the director, that will be 4% less than the length of dipole, that is 4% of 96% of 2.131, that comes out to be 2.22 meter. And the length of reflector should be 5% more than the length of driven element, it is 105% of 2.31, that comes out to be 2.43 lambda. Now directed spacing, that will be 0.13 lambda, and reflected dipole spacing, that will be 0.25 lambda. Just put this value lambda here, you will get these are the design equations for designing a Yaguda antenna. Now see, so this one is the radiation pattern of Yaguda antenna, in which this unidirectional, in which having a higher gain and higher directivity as compared to the very small side lobe or back lobe. Clear? So what are the applications generally used for the TV receptions, and where it is used where a single frequency application is needed. Now what are the modifications done to the Yaguda antenna? What are the modifications done to a Yaguda antenna such that its characteristics will be better than the normal Yaguda antenna? Means if I say this Yaguda antenna have some gain and bandwidth, clear? So I want, if I say this Yaguda, I want to have a more gain, and so what are the modifications done to the Yaguda antenna such that it or you can say it is a upgraded version of the Yaguda antenna. Clear? So first is we can obtain the circular polarization for with the Yaguda antenna. What is circular polarization? Circular polarization is Ex component and Ey component, that should be equal to 1. In दोनों का ratio, that should be equal to 1. That's why it is known as a circular polarization. And for the satellite communication, we always prefer to have a circular polarization. Clear? Because even after disturbing the polarization, the electric field strength in x direction and electric field strength in the y direction will remain always same. Clear? Even after disturbance due to the atmosphere. That's why we always prefer to have a circular polarization, because horizontal polarization, if I say this is a transmitter and this transmitter is transmitting a horizontal polarization signal, but if I say at the receiver we have a receiver which receives a vertical polarization, then this horizontal polarization signal cannot be received by the vertical polarized receiver. Clear? So to get the general, we always prefer to have a circular polarization. Clear? Now see this one. In circular polarization, देखिए, see, driven element is now what? Helix, in the form of helix. This is the driven element, and these are the cross detectors. One is placed like this one, this one. These are act as a cross detectors and directors which increases the directivity, and this helical antenna produces a circular polarization, and this will act as a what? Reflector. Clear? So this one is the modification done to the Yaguda antenna. Another one is the Darfur shaped dipole antenna. In this we have analyzed that Yaguda antenna, length of Yaguda antenna, driven element, length of the driven, if I changes the length of the driven element, then the radiation pattern will also get changed. Now see this one. Why? If I say the length of dipole is increases to 3/2 lambda, then its radiation pattern will be like this one. Now if I say this 3/2 lambda, if I say this length is getting increased to lambda by 4 and this one is lambda by 2, then we will get this type of radiation pattern. Clear? Now to have a unidirectional radiation pattern and with no side lobe, this driven element shaped is given to this one, and similarly for reflector under the director. Clear? And the spacing design equations is given like this one, and this one is the length of reflector is 1.3 lambda. Clear? So to change the shape of driven element and length of driven element, reflectant driven element, we will get the unidirectional radiation pattern, and this shape is known as the Darfur shaped dipole antenna. Clear? Now next one is the square corner Yaguda antenna. In this, similarly, this one is the driven element. This one is what? Driven element here. Clear? And these are the directors. So you can say, if I say this one is here, these are the driven element and these are the director, and these are act as a reflector. It is just like this one. Reflectors are like this one, and in the front of this one. Clear? So this one, or you can say these are the act as a reflector, and in between there is a driven element with this, and directors are also attached to this one. So this one is the square corner Yaguda antenna. Now next topic is the long wire antennas. What are the long wire antennas? Long wire antennas are the antennas which having a length is more than the half wave length, means the length of the antenna is greater than the lambda by 2, or you can say n times the lambda by 2. Clear? So this one, So long wire antennas are the having a length which is greater than the lambda by 2 or multiple of lambda by 2. Clear? Now these long wire antennas are of two types, resonant antennas and the non-resonant antennas. You see this one. What are the resonant antennas? You will see that, observe that in the non-resonant antennas there is a terminal impedance and there is no terminal impedance. So when there is a terminal impedance means there will be no existence of standing waves, and the whole power which is supplied to this one will getting radiated into the space. It means there will be no reflection from the space, and it means that the radiation pattern will be unidirectional. Clear? And in this there is no impedance matching with the space, means there is no terminal impedance, means there is no impedance matching. It means the wave which is getting forwarded and will also get reflected back by the space, and there will be existence of standing waves. That's why its radiation pattern will be in the forward direction and some will be in the backward direction. That means it's have a radiation pattern of bidirectional, and it is having a radiation pattern is unidirectional. Clear? So long wire antennas are of two types, long wire antennas, resonant and unterminated, and another one is the non-resonant, that is a terminated. So resonant antennas are those in which the standing waves exist, absence of terminal impedance, hence there is no matching, direction pattern is bidirectional. In resonant antennas, the wave move in forward direction, they do not form a standing waves. Clear? So therefore the radiation pattern is unidirectional and all wave will move in the forward direction only. Clear? And the third next point is the impedance is matched due to the presence of the terminal impedance. Clear? So in the long wire antennas, first we will discuss about the V antenna. In the V antenna means this one is the first long wire antenna. If I say this one is the long wire antenna and another one is this one long wire antenna, these long wire antennas are arranged in such a way that it forms a V shape, and the angle between these two will determine the overall radiation pattern of the V shape antenna. Clear? Now as you see that there is no terminal impedance matching. Is there any terminal impedance matching? There may be, there may not be. Clear? And this is a source impedance matching. This is source impedance. Clear? So we'll see that the angle between these two elements alpha, and this is a input line. यहाँ से हम excitation provide कर रहे हैं. Clear? So this angle between these two dipoles will determine the radiation pattern of the antenna. Clear? Now see this one, as this dipole is unterminated means there may be a radiation is length is this one, there may be a radiation pattern of like this one. Clear? Now overall radiation pattern will be what? As we know that this radiation pattern will be equal to what? Overall you will see that this B plus B dash will get added, and this D plus D dash will also be get added. Clear? And this A dash direction is in this direction, A is in this direction, C is in this, and C plus. So overall you will get this. These are the minor lobes and this is a major lobe. So overall radiation pattern will be what? Bidirectional. Clear? So if I want to convert this V-shaped pattern into a unidirectional, we just put the impedance matching at this one. When I put the impedance matching is this one, so you will get the overall radiation pattern will be unidirectional. Clear? The book I have referred for preparing the slides, that is Antennas for All Applications by J.D. Cross, and another one is Antenna Theory, Analysis and Design by the Balanese, 3rd edition. Thank you.